Hi everyone. I thought it would be a good idea to look at carbon dioxide and oxygen calculations and formulas that we'll be using in this course. So I prepared this review for you, and I hope this is good information for you. We'll start with looking at carbon dioxide values, which we can use to determine our dead space calculation. So this is a review of dead space and the way we're able to calculate it using carbon dioxide. Just as a reminder, we have the airways, have alveoli. This alveoli is perfused. We have perfusion. You see the patent capillary bed. But this alveoli does not have perfusion. Okay, so we'll talk about that in a little bit, but just note the difference. As a quick review, anatomic dead space can be calculated at approximately 1 milliliter per pound of ideal body weight. So the anatomic dead space that all of us have residing within the airways as a reservoir, we can take the patient's ideal body weight. The patient weighs 150 pounds, then they'll have 150 milliliters of dead space. That should represent approximately 35 to 45% of that patient's inspired tidal volume. Anywhere from a third to about half of the tidal volume will reside in the airways. That's important to remember because we have to clear our dead space before that volume actually fills the alveoli as alveolar volume. Alveolar volume is the most important because that's what is actually taking part in gas exchange. If we take the patient's anatomic dead space that resides in the airways and add to it alveolar dead space, then we can determine the patient's total physiologic dead space. So again, physiologic dead space is the anatomic dead space in the airways and reservoir added to any alveolar dead space the patient may have. So if we look back down here at our alveoli, remember we said this alveoli was perfused, but this alveoli was not. Many reasons perhaps for us to not perfuse this alveoli. Maybe the patient is hypovolemic. Maybe this patient's on a mechanical ventilator and we have actual dynamic compression of the alveoli against the capillary bed. Whatever the reason is, no perfusion, adequate alveolar volume, that's ventilation in excess of perfusion, that's what dead space is. So if we take any alveolar dead space added to the anatomic dead space, then we get physiologic dead space. To determine physiologic dead space, we can't take this 1 mil per pound because now we're having to incorporate the amount of alveolar dead space. We actually have to use an invasive measurement, PaCO2. And from our invasive PaCO2 value, we can subtract our PeCO2. Now E has a line over it, E being exhaled CO2, and it's the mean, so we're actually using capnometry here. So and PaCO2 from a blood gas, the PeCO2 from capnometry, and we'll take that difference and place it back over the PaCO2 again to determine the actual amount of dead space ventilation that's taking place. So I have some calculations for us to look at. Again, physiologic dead space is the total amount of dead space. We'll take the patient's blood gas values and we see that the PaCO2 is 40 torr. And from capnometry, we have both end-tidal CO2 and a mean exhaled CO2. So we need to be very careful. You see here I've got an asterisk pointing towards the mean exhaled CO2. Make sure that you obtain that value to plug into your formula, not the end-tidal value. These two are different. End-tidal is the highest amount of CO2 exhaled. Mean exhaled would be an average of these values. So always take the average. So I've got PaCO2 of 40 minus the average of 30 that we got from capnometry, back over 40, which gives us 10 over 40 or 0.25, 1/4. So we've actually taken the PaCO2, the PeCO2, and determined the patient's physiologic dead space is approximately 25%. Okay, I took this one step further down here, and I want to take this percentage of dead space that we have that does not take part in gas exchange and determine how much volume that is. So remember, in the earlier part of this presentation, we said that if we take our total volume, not all that total volume reaches the alveoli. The reason being we have to clear dead space first. The remainder amount is actually what enters the alveoli. So you'll see this down here, quick formula that we'll look at in just a second. But what I'm taking is our total volume, 800 milliliters is what I am using, just for easy math, multiplying that by 25%, which is the physiologic dead space. If my total volume is 800 milliliters and 25% of that is dead space, then when I do the math, I can find out how much volume that is, 200 milliliters. So down here, I took my total volume of 800 milliliters, I've subtracted my 200 milliliters of dead space volume, and the remainder is how much is taking part in gas exchange, which is my alveolar volume. Okay? The reason I think this is important, we can look at here. Pardon me. This drawing is supposed to be an eyeball, nose, and lips. So this shows us that the patient has airways and alveoli. So when I inspire gas, that total volume is the total volume, which is divided between dead space volume and alveolar volume. Okay, so I have the quick equations. This is what we looked at before. Total volume minus dead space is alveolar volume. I can take these same variables, add them together, and say that our alveolar volume plus dead space volume is total volume. So you've looked at these before. It's probably just been a while. It's just as a refresher. If I take these separate volumes, remember multiplying by frequency, we can find out what minute ventilation is occurring for each one of these. Total volume frequency, minute ventilation, dead space times frequency is dead space ventilation over a minute. Alveolar volume times frequency is alveolar ventilation over a minute. I could also say that my minute ventilation is equal to my dead space ventilation plus my alveolar ventilation. We could do that as well. Here's the problem with dead space, and this is why I wanted to create this lesson and review this with you really quickly. Problems with dead space can be encountered with rapid shallow breathing. As your total volume decreases, even with an increase in frequency to maintain the same minute ventilation, the patient's alveolar ventilation can still decrease, causing their CO2 to rise, which is respiratory failure. Okay? So to make that make a little bit clearer sense, I just plugged in some values here. We have two patients, patient A and patient B. Patient A has a total volume of 500 times a frequency of 10, so the total minute ventilation is 5,000 mils. Patient B, total volume of 200 mils times a frequency of 25, still gives the same minute ventilation. So both patients, A and B, appear to have the same minute ventilation. However, look what happens when we subtract the dead space volume. Assuming that each of these two patients has the same dead space volume, patient A with a total volume of 500 minus the dead space of 200 would give an alveolar volume of 300. Remember, they're breathing at a frequency of 10, so alveolar volume times frequency gives alveolar ventilation, which is 3,000 milliliters. Patient B with a total volume of 200 mils, remember their dead space volume is the same, 200 minus 200 gives an alveolar volume of 0. So even with this faster frequency compensating and giving us what looks like the same ventilation amount, when you look at this patient's alveolar ventilation at 0, you can see there's a drastic difference. Okay? So again, when we talk about dead space, we have anatomic dead space, but also alveolar dead space. Added together, we get physiologic dead space. If the physiologic dead space equal or exceeds the patient's total volume, they're actually not ventilating even though they may appear to be. Their CO2 will rise, again causing respiratory failure. All right, that's the conclusion of this part of the CO2 O2 formulas lesson. And if you have any questions, please let me know.